And so basically the reason I chose Cape D'Agula is it's a marine reserve from where I'm from, okay? I'm from Hong Kong, and this is what it looks like. I see this every night, okay? This is from my bedroom. Yeah. Okay? But this is actually where I work. So this is the Swire Institute of Marine Science. And this area here is Hong Kong's only marine reserve, which is why I'm telling you this story. And it's the only marine reserve where there is a complete no-take zone. Hong Kong is a very unusual place. We have a lot of protected country park for terrestrial environment, but very little protected area for marine environment. So we have this tiny marine reserve, and it's the only place where the sea urchins aren't fished. So this actually is a real story. It's about trying to look at, is the marine reserve effective at protecting the sea urchins? So that's the reason. And I want to show you some pictures of Hong Kong. That's the other reason I did it, okay? So the marine reserve was enacted in 1996. And so if you like, for our hypothetical question, I want us to be able to assess the distribution and abundance of sea urchins in the intertidal area in the marine reserve to see if there are more in the marine reserve than there are outside the marine reserve, which is where there's fishing. Okay, so that's a sort of image to keep in your mind, the sort of way we're thinking about it. Now that's quite easy if we're dealing with a very small area. Okay, so these black things, okay, they're sea urchins, they're in a rock pool. You can count how many is in the rock pool. It's easy, right? 46, okay, per meter squared, okay? But when we get to the marine reserve, and the marine reserve is very tiny, just goes around this area here, okay, you can see this delimits the area. When we get to the marine reserve, of course, we can't count them all. It's impossible. So this is coming down now to the population. How do we manage to get an assessment of the population, the abundance of the sea urchins in this marine reserve area? We can't count them all. A, we don't have the time. B, they move around, okay? They're not like the mussels we just saw, which sit there and do nothing. Okay, these sea urchins, they move around, and so if you start counting them on day one, they're all following around because they like to be counted on day two. Okay, so you can't do it that way. So what we need to do is we need to take some sort of sample of them which is representative of the true population. We can't count the entire population. We can't count the true population. But we need to try and get an assessment which is representative. That's that first R word. Okay? It's got to be a true representation of the population of sea urchins in that reserve. So how can we go about that? Well, first of all, we really need to think about what are the end results we want to achieve. Remember I said you've always got to plan how your analysis will go, what statistics you'll use before you do any measurements at all. You've got to think about what are the ways that I can measure the population which will be useful and which I can use then to try and go ahead. And as you all know, as I said, I'm preaching to the converted. I know a lot of you have done this. The major thing we need to know is to know the average number of sea urchins in an area, and we need to know the range of variation around those averages. So we need to know those two things. We're trying to work out the average and the range around that average, the variance. But also, the other thing we really need to know is how good our estimates are. How good are we at estimating that population? Because we also need to know how reliable, remember that's the second R word, how reliable our estimates of that population are. So what are these things we're trying to measure? Well, technically people will tell you that most biological data is normally distributed. You've all seen this before. And here are two different populations. They've got these normal distribution curves, and we can see they have two central points or central tendencies. These two populations have got different central tendencies. And we call the central tendency the... Yeah, it's so exciting, isn't it? The mean. Okay, so that's one thing we want to calculate, okay? We want to calculate the average, or in statistical terms, that would be the mean of the population, okay? And that would be the mean density or abundance per area, okay? So that's one of the things we're trying to achieve. The other thing we're trying to achieve is some measure of spread around that mean value. And the measure of spread is called variance, and we can measure it as, sorry? Sample variance here, but I'll come to that in a moment. Variance, that's just, standard deviation. We'll stick with variance for the moment anyway. These are three populations, okay? They're three populations of little yellow sea urchins, okay? Same numbers of sea urchins in all the populations, But basically, the only difference between these populations, they've all got the same mean, if you look down here, is actually in the spread around those populations. The variance is different. And that's because in the bottom population, in some areas, there are very dense clumps of these sea urchins, and in some areas, there are very few of them. And so we have a much wider spread of distribution around that mean value. I've never seen anyone get excited about this before. So that's the other thing we're trying to get a handle on. The average, or the central tendency, and then the spread, or variance, or variation around that central tendency. And as somebody said just down here, we can convert the variance into something which we call standard deviation. And standard deviation allows you to know how much of the population falls within -1 or +1 of the population, and that's about 68.26%, or how much the population falls between -2 and +2 standard deviations of the mean. Anyone got an idea? Plus or minus 2 standard deviations? How much of the population falls? No, 95.7832. So, about 95, exactly right, yeah? So these are things we're trying to measure, okay? These are what we want to get representative measures of, which we need to know, are they representative? We also need to know, are they reliable? Are they trustworthy in how we've collected that data and the results which we get? So these are the two things we're trying to measure. And as I said, variance and standard deviation, we can actually use those to calculate each other from. So you know that before, yeah? You've done mean standard deviations endless times, yeah? You're bored with them. Yes? Nobody said no. Do you all know what a standard error is? I won't ask you what standard error is. Do you all know what standard error is? Yeah. Okay, what's that? Okay, just kidding. Okay, so how do we do this? Okay, well, as I said, we're going to take these samples to try and estimate the true values. But I said we're going to talk about how we can do it well, and we can talk about how we can do it badly. And so I think that the problems we have depend on three principal things. The first is how we score the variable, okay? How we actually score those counts we're going to make. The second is how many of these counts we take, and we call these counts replicates. And the third is how the replicates are taken. So we're going to go through 1, 2, 3 to try and see how we can do it badly, and then try and have suggestions for how we can do it well. So let's have a think about it. What are the errors that we can make, first of all, when we're trying to score the variable? In this case, the variable is the number of sea urchins in an area. And there are a number of very simple errors we can make. First, there's errors of identification. So it's, can we all identify a sea urchin? Can you identify a sea urchin? Yes? Okay, we've got 3 sea urchins there. Which one are we working on? Well, we're actually working on this one, okay? This one is something called Anthocedaris crassispina. And I gave it its scientific name because, as you all know, scientific names are unique. The trouble is, in many parts of the world, there are not keys to identify species. You have to try and go to local names, or you have to go to museums to be able to find out just exactly what that species is. And so when we're doing large-scale surveys, and it's something Nova may touch about, one of the first principal things is, can we identify the species which we're working on? I know for a fact that one of the species I spent working 20 years on in Hong Kong, we've been calling it the wrong name for 20 years. That's not bad, actually. 20 years for me isn't bad. It's usually a lot longer, so I was quite pleased with that. But we have these problems. Obviously here, you've got fantastic books, you've got keys to identify things, but in other parts of the world, they simply don't exist. And so you first of all have a very basic problem of, can we identify what the species is, and can we give it a scientific name? So that's a very simple thing to start with. The second thing is, if we can give it a name, is, can you all identify that sea urchin in the same way? Now you've been all out, I think you've been out doing counts on the shore, is that right? Do you trust the data your friends collected? Yeah? No? How do you think you did? The species were quite easy to ID? Did you find that easy? Yeah? Did anyone find it difficult? Yeah, okay, that's right. Yeah, okay, it's a little bit iffy. You're thinking, ooh, species A. No, you can't say species A. You've got to use scientific names. So there is an issue as well about simply how to identify species. So even these simple things, here in Boston, it should be easy, or a lot easier. You've got great textbooks, you've got great guidebooks. Once you get outside here, if you go to the wilds of South Carolina or somewhere, then it's much harder, okay, because they haven't got electricity yet. Why do you think Brian's here, okay? He loves his toys. He needs to come here for electricity. Okay, so there's lots of errors simply about things about how we can simply count these organisms, okay? So it's a trivial issue here because you can probably do it all quite well. You've got the resources. In many parts of the world, those resources don't actually exist. And so you need to find ways of making sure when you do count an organism that everybody counts it in the same way. You're identifying those same organisms. So these are very important things to do. The other issue is how do we count, or how do we decide to count what sort of area that we're going to count organisms in? If we use a 25 by 25 centimeter quadrat, for example, depending on which organisms we're working on, we'll get very different types of scores. It's very easy, for example, to count snails in here, but obviously you have a little bit of a problem when you have 0.3 of an elephant, okay? So when we're counting these different organisms, of course, the scale that we're working on is very important. And there are methods to work out what is the appropriate size of sampling unit you should use when you're sampling these organisms. Snails, very often we use something like this, 25 by 25 centimeters. Elephants, we use hectares, and you go up in helicopters and it's really cool, okay? And you go around buzzing elephants, okay? So it's very important to think of scale when we're looking at these types of things. So we've got this idea we're going to count within a unit, okay, this unit. Actually, I do apologize to you. I didn't introduce you to this. This is one of the wonders of modern science, okay? This is, you know, I said about rocket science. Well, this is it, okay? This is called a quadrat, okay? Or quadrat, okay? And it's a beautiful thing to see. It's beautifully tooled, okay? You can buy these in any very, very well advanced hardware shops. And you put your quadrat down, okay? That's interactive teaching. All right, do you enjoy that? You put your quadrat down, and what you do is you then count the numbers of organisms in that quadrat. So, sea urchins. That's a sea urchin, okay? How many? Yeah, 6. Well done. So the point is, very simple thing. We just put a quadrat down. We just ask you how many urchins are in there. We got at least 3 or 4 different answers, okay? It's not repeatable. It's not reliable. Okay? So if we have the group of urchin haters, the urchin haters would say 1. Okay? Because that quadrat's only got 1 full urchin in. If we get the urchin lovers in, and I don't know where on the fence you fall, okay? Something you're going to have to work out amongst yourselves. If you've got the urchin lovers in, what you find they'll do, they go, oh, I've got a half here and I've got a half there, and if I join them, I'll get a whole. Yeah, score. So you've got different ways of trying to do this. And this is it's a trivial example, but it does give you the ideas of where you can make some really big mistakes. If one group working on an area which you're trying to protect hates sea urchins, you get 1. Another group working in the area which is going to develop, you might get 5. And they say, look, they're so different. We must stop development. Well, actually, they're the same. You just counted them in a different way. So this is where we need to get to just make some basic ground rules. We need to make sure that our counts are repeatable. We need to make sure everybody can count them in exactly the same way. And there are a number of ways you can do that. It actually doesn't matter much as long as you are consistent and that everybody knows what you're doing. Some people, they like to count 2 sides of a quadrat. So in this case, 1, 2, 3 sea urchins. You don't count the ones along here. Some people, they just like to go more than 50%. But that gets a bit iffy. I mean, 50% of a sea urchin? Sometimes difficult to tell. But the important thing about this is that you do it in a way which is repeatable and everyone does it in the same way. So when we all look at this, we would all say there is 3 sea urchins in this quadrat. Yes? See, we're getting there, aren't we? We're sort of ambivalent about sea urchins now. We're not lovers or haters, we're scientists, okay? So that's the way we can do it. So these are small issues about thinking about how you can make mistakes and how you can fix those mistakes. So in this case, it's all about making a counting rule and making sure it's written in your materials and methods. You've thought about it before you go out. You can't make this decision halfway through your sample. You can't go, oh, damn. And you can't just sort of go, oh, I'll just 2. Okay? You can't do that. You've got to make sure before you go out, you've sorted out all these problems.